Welcome everybody to this month's Southern Alberta ITE luncheon webinar. As you might have known or seen, our webinar platform has changed. We're now using Google Meet. This allows us to have several additional presenters from our presentation. So as part of that, Google Meet is kind of similar to Skype and Project Teams. So we ask viewers to please mute your microphone during the presentation. And Q&A answer period we held at the end of the presentation. So if you could please use your chat function at the end of the presentation, and we'll make sure the questions are asked in orderly fashion. That way we can ask the viewers to unmute their mic and ask the questions directly. Before presentation, just a quick note. Congratulations and welcome to the newly elected president of the University of Calgary ITE Student Chapter, Marcellus Lopez, a PhD candidate at the University of Calgary. And a thank you to the past president, Jacob Lam. So our presentation today is from the University of Calgary's fourth year engineering students on their ENCI 570 Capstone project. It's for the development of a pedestrian system plan for the interface with the University of Calgary campus. We have 6 presenters today. The first presenter would be May Hassinen, who is in her final year of civil engineering undergrad. She has experienced transportation and geotechnical aspects of engineering through internships at GeoGrout and Keller Foundations, as well as her participation in the Capstone project. She is passionate about applying what she has learned through her degree towards new and innovative projects. The next presenter would be Catalina Barreto, who just graduated from civil engineering with a minor in transportation. She completed an internship in construction management with PCL. Her main focus during the Capstone project was the development of user sensitivity parameters employed for the utility function analysis of the network. Next presenter after that will be Sad Khurshid, who graduated from civil engineering with a GPA of 3.92 and currently working at Power Engineering. He completed an internship at Altalink, as well as research work in many engineering fields, including transportation engineering. Sad's main responsibility in the Capstone project was to lead the development of the TRANSCAD model. After that is Ala Abdallah, who graduated from civil engineering with a minor in structural engineering. She completed an internship with also road construction as an assistant estimator. Her main responsibility in the Capstone project was cost estimation, as well as various design elements for problem areas, such as traffic calming and sidewalk enhancements. Next is Morgan Grab. Oops, what's going on? Who graduated from civil engineering and currently works for Lafarge Canada in the road construction industry and has over 2 years of construction estimation experience. Morgan was involved on the Capstone project in the creation of design criteria and choosing the final design elements. And lastly would be Zachary Reddick, who will graduate in the fall of 2020. He has completed 2 different summer internships in both geotechnical and transportation engineering, as well as a year-long internship at Modern Niagara to gain experience in project management and mechanical engineering. With that, I leave you to the team and the presentation.
Thank you, Lou, for that introduction. Hi, everyone. Hi, everyone. My name is May, and I will be introducing our ENCI 570 project for you today. With me, sorry, did you get the presentation up? Perfect. Sorry. Okay. So with me today, I have Ala, Zachary, Morgan, Saad, and Catalina. Unfortunately, Fadi and Cassidy couldn't be here with us today. I'd also like to give a special thanks to our academic advisor, Dr. Hunt, and our industry advisor, Monique Castonguay, for overlooking this project. So to begin this presentation, I will be giving a brief introduction to the project, then we'll be moving into the project process, findings, applications, and finally the lessons learned and next steps. First, I'd like to talk about what exactly ENCI 570 is. ENCI 570 is a year-long group design project that allows students to take the engineering and project management principles that they've obtained over the course of their degree and apply them to real-world design problems. With the supervision of an academic advisor and an industry advisor, each team takes on a project that focuses on a different problem. This project also allows students to build team management and leadership skills through rotating project manager positions and sub-teamwork. Each team was required to submit a project proposal, fall semester report and presentation, final report, and final presentation poster. Overall, our team received an A grade for this project. The pedestrian mode system is held out to be the foundation of Calgary's transportation system. Our project focused on improving the pedestrian user experience in and around the University of Calgary by designing a system that encourages users to use active modes of transportation, such as walking and cycling, when commuting to and from campus. This would be done through designing and evaluating a new and improved pedestrian infrastructure system. This new system would then help reduce pedestrian-related incidents in and around campus as well. The development of a recommended plan included network design and evaluation, consideration for distance minimization, levels of pedestrian access, and existing opportunities and constraints. It was important to create a method to quantify the benefits of pedestrian infrastructure improvements in a dollar value. Potential networks were evaluated based on cost-benefit ratios, safety, and several other elements that will be discussed later on in this presentation. Now I will pass the presentation on to Catalina, who will talk a little bit about the project process.
All right, thank you, May. Hi, I'm Catalina, and in the next portion of the presentation, we'll be moving into the steps taken in the project, and I'll kind of go into a little bit of detail with Saad about the analysis section as well. So this graphic here shows an overview of the main stages of the project. In the early stages of the project, we took inventory of all of the existing pedestrian facilities and the conditions in the area and conducted a literature review of established design standards and guidelines currently in use. We then documented all of those existing conditions electronically in a series of maps using Google Earth, ArcGIS, and then eventually that goes into TRANSCAD. We examined features such as the pedestrian crossing types, walkway conditions, accessibility features, snow and ice clearing, and pedestrian scale lighting to determine typical issues and where some of those things might be lacking. The quantitative analysis then consisted of our two main components, the utility function and our TRANSCAD model, which will be discussed coming up shortly here. And finally, the vision plan contained our findings, our recommendations, and an analysis of the social benefits of improvements compared to their costs of implementation. All right, so with our, sorry, Morgan, if you could just, thank you. So the first step in our project was to establish a boundary for our area of study, which will be referred to as the halo area. It's outlined in red on this map here, and we broke it up into smaller communities, which are the communities surrounding the U of C, just to make it kind of more manageable for study and kind of divided amongst the team. Next, we began documenting the conditions in each community with a preliminary desktop review using Google Earth and just kind of Street View, find certain issues. And we followed that up with site visits to make sure things were up to date and pinpoint certain things that we couldn't find electronically. We then used that information to create an inventory report highlighting the features of the pedestrian network. With a full inventory of existing pedestrian facilities, we were able to identify potential issues to address over the course of the project. Then we followed up on those selected areas of concern as needed. And finally, the data marked up on Google Earth was transferred to ArcGIS to better organize it into our collection of formal maps, like the one pictured. And then we had maps for lighting and accessibility features and all of the other features that I mentioned earlier. All right, so a main goal with our analysis was to try to really quantify the benefits of the user to the user of different features of a pedestrian network, such as changing the light spacing or type of path or things like that. So the first step we took to do that was to build our utility function. So we measured how much users preferred certain pedestrian network features and converted this to a money equivalent to determine the cost of a trip to a user. While doing this, the existing conditions data was used to build a pedestrian scale traffic model in TRANSCAD, which Saad will talk about shortly here. The utility values were integrated into this model next in order to calculate the user cost of travel through the network. And again, Saad will talk about the calculations and all of the components of that. And then finally, for future applications, this model could be used to kind of iterate different solutions and find the optimal one there. So now I'll just be going into depth about the utility function. So this is kind of our user interface that we created. And so we did this in order to quantify our user preferences in kind of a sort of survey that we ourselves as the team members performed. So what you see here, the user interface that we used to collect the data, we examined 6 different walkway characteristics. Just from left to right, it's the facility type, so like the type of pathway, the crossing conditions, the walking distance that the user would have had to walk, the pavement quality or condition, so whether it's cracked or good, smooth, lighting conditions, including the lighting spacing or whether there wasn't lighting, and then whether that area was included in the snow and ice clearing plan. So each of these characteristics had several options assigned to them, and this created combinations of about 15,000 different possible routes that a user could rank when going through this ranking exercise. So how this works is that it generates 4 random route options out of that pool and tasks the user with ranking them from best to worst, with 1 being the best and 4 being the worst. This could be repeated with automatic buttons to generate new conditions and to save the rankings. So for our case, we repeated this 100 times each between the 8 of us to generate our big data pool for analysis and to determine the preferences for each option. Sorry. And now I'll be moving on to the results of that. So once we had our big data set, we used BioGene, which is a tool used in Python, to perform a maximum likelihood estimation on our data set. We ran BioGene with all of our data, and from it got our utility sensitivity values, which you see in the 3rd column here. This table shows just a small portion of our outputs, just for discussion's sake. So we then converted these sensitivities into cost using a cost conversion that we got from a literature value. That we got from a literature value and that we scaled to fit our data. And how we did that was that the literature values from a previous study had similar utility features, as well as they had also looked at cost in their survey, so to speak. And we were able to convert that to scale to our data. So as you can see here, once we had converted it to cost in our 4th column, the cost of, say, crossing a major road at an unsigned, non-painted crossing is much higher of a cost to the user than crossing an overhead flashing beacon crossing. As a pedestrian, that might sound similar to or familiar to you. Just for safety reasons, it feels a lot safer to be crossing somewhere signalized. So one thing to note is that crossing type is a unique category as it does not account for the distance traveled by the user. All of our other things like lighting and the pathway types, the facility types and such, they include the amount of time or the distance that the user has to travel along it. So the cost increases the longer you're walking on it. So that is kind of shown in the bottom 2 rows there. You've got the grass trail is obviously a higher cost, more of a pain to walk on than a paved sidewalk. All right, so after generating those utility cost equivalent values, we created a spreadsheet in order to kind of focus in on the benefit of a single individual navigating in our specific problem areas. So basically we use this sheet here to manually input the details of a route. Say in this case, this had 2 of a certain type of crossing, and then in a different part of the sheet, they were walking 300 meters along a certain area. So Ala will walk us through a sample manual calculation for one of our problem areas to show you kind of how this sheet works. And this calculation is on a small level, but it represents kind of what's being done on a bigger scale in our TRANSCAD model as well. Next slide, please. All right, so another thing to note is that the team assigned sort of a baseline utility and utility cost equivalent values to our network. So we called this our gold standard utility and define it as the utility that a path would have if improved to the best possible user experience conditions. So it's based on using the facility type that's practical in the current context with the best utility and with ideal conditions for lighting, snow clearing, and path quality. So this slide here lists the features assigned as gold standard and their utility and their cost equivalents. So as you can see here, like 30-meter pedestrian scale lighting is the ideal, and signalized crossings are ideal, and having a median to separate you from the road is an ideal condition for pedestrian. And we use this for comparison later on. And now I'll pass it on to Saad to talk about our TRANSCAD model.
Thank you, Catalina. Today I'll talk about the TRANSCAD model. The TRANSCAD is the transportation engineering software, which allows transportation modeling and transportation analysis. It's kind of like ArcGIS, except it also has traffic planning and modeling capabilities. So one of the main goals of this project is to quantify the benefits to society of all the improvements we made. In order to find out the total societal cost of the pedestrian system, we need to model the number of people who travel on our path in our system and multiply it by the utility cost of that path in dollars per trip. The difference in total societal cost between the current scenario and the scenario with our pedestrian network improvements is the benefit of the improvements. We decided to create this model in TRANSCAD, which, as I mentioned, is like ArcGIS with traffic analysis and planning capabilities. Using TRANSCAD, we can create a pedestrian network, fill in the network with network attributes such as facility type, snow clearing, lighting, and crosswalk type, and use these network attributes to calculate the societal cost of every link in the system in dollars per trip. We also added known pedestrian flow data to the model. Using the pedestrian flow data, the pedestrian network, including the centroids, which are involved in origin destination matrix estimation, as well as the costs for every link in the system, TRANSCAD can estimate an origin destination matrix or an OD matrix and assign traffic flows for every single link in the system. Once we got the traffic flows on every link, we multiply it by the societal cost in dollars per trip for every link and get the total societal cost of the system. As mentioned, the total societal cost can help you determine the benefits of that improvement. And next, please. Okay, so in the next few slides, I'll go into some more details in the process. We first created a pedestrian path network, and we inserted network attributes such as snow clearing, lighting, pavement conditions, facility types, and road crossing types for every link in our system. As we did not obtain a GIS or geographical information system from the city, we had to manually determine these parameters from publicly available data as well as Google Earth. As we had over 1,000 links in our system, this was a relatively large task. Next, please. One way to estimate origin destination matrices is through the 4-step transportation planning process, which involves estimating generations and attractions through employment and population data. The other option that we have available is to estimate origin destination matrices from traffic counts. So we decided to estimate the origin destination matrices from traffic counts as it provides more granularity. We obtained traffic data from the City of Calgary's Caltrans system, as well as Calgary Transit data, and we loaded it into TRANSCAD. we had traffic count data from more than 100 locations. As expected, we had high traffic counts from the area around the LRT stations and near the university. Next, please. Once we got the traffic counts, we need to create origin and destination centroids, which is basically points from which pedestrians are generated and removed from the system. And they're shown in the map in yellow. We place centroids at LRT stations, major bus stops, major generators and attractions of pedestrians, such as the hospital or MCMAHON Stadium, and as well as random locations in every community in the study area, as well as at study area boundaries. We place the study area boundaries so that we can account for people who are exiting or leaving the study area on foot. Once we created the centroid using the TRANSCAD origin destination matrix estimation process, it's basically an algorithm. We estimated an origin destination matrix, and from the origin destination matrix, we assigned traffic flows, pedestrian traffic flows, for every link in our system. This is a really big step because normally it's not easy to tell how much traffic flows there is anywhere without doing a traffic count. So this is a really cool way of estimating. Next slide, please. So this is our map of outputs. This is our estimate for the 24-hour pedestrian flows. And as mentioned previously, the areas around the University of Calgary have higher pedestrian flows. This is the kind of the peachish color, while little residential plots in Varsity or in University Heights, which are shown in black, tend to have lower pedestrian flows. One thing though that's really important to understand with this is an estimation. This is not this is an estimation. This is an estimation with pretty large errors. However, this can give us a bit of an idea of what sort of areas you get higher pedestrian flows and what sort of areas you get lower pedestrian flows. I will be talking a bit later in the presentation about some more cool things we can do with TRANSCAD. I'll pass on to Alla to now talk about the problem areas.
Thank you, Sad. Okay, so now just to summarize the entire project process, we will be showing you guys an example. Overall, through our area of study, we identified a total of 8 problem areas as highlighted in red on this map. However, for the purpose of this presentation, we will only be going through the process of one problem area as an example, and then Morgan will be showing the improvements of 2 other areas. So the first area we're going to take a look at is the BRENTWOOD Station pathway. So the first step, as mentioned earlier by Catalina, was to take inventory of the existing conditions. Multiple site visits were conducted along this pathway that is heavily used by a lot of people. That red line marked out on the map on the right is a steep mulch path that leads up to an uneven asphalt path marked out in yellow and shown in the image on the left. So people are walking along this uneven pathway with wide cracks as shown in the picture. And during the winter, the pathway also becomes very muddy and slippery, which gives rise to a lot of safety hazards. In addition, there is insufficient lighting along the entire length of the pathway. So at nighttime, a lot of people will feel scared, unsafe, and unaware of the large protruding cracks that may cause some tripping hazards. So the second step is the utility function analysis. Each problem area was analyzed using the calculated utility sensitivity values. For example, each description is given its own unique utility sensitivity value, and the more negative the value, then the more undesirable it is to the pedestrian. The blue column, it represents the distances that we measured using ArcGIS and site visits. So for example, the 300 meters is the yellow line marked out on the map representing that crumbling asphalt pathway we showed earlier. And the 65 meters is representing the red line marked out on the pathway of the grass trail along the minor road. Lastly, the entire path has no lighting, therefore was inputted as 365 meters with no streetlights. These values were then converted into a dollar value using the money sensitivity value. A higher dollar value means a higher cost to the pedestrian. So as seen in the existing conditions of this pathway, it results in a utility function societal cost of $4.85 per trip, and our goal is to actually reduce this high cost. So in order to reduce the cost, we implemented overall 3 different plans for each problem area. For this specific problem area, we will be showing you guys only the long-term plan that we came up with. These improvements consisted of tearing out the asphalt pathway and replacing it with a concrete one with mesh reinforcement. So that would ensure a smoother surface and a longer lifespan. It also consisted of adding in 2 wheelchair ramps as shown in pink on the map where the pathway meets the road. Along the entire length of the pathway, we added in some lighting to create optimal visibility for the pedestrians, and 2 emergency call towers were installed to make the area safer as shown in blue on the map. The lighting can make a safer zone for the pedestrians in terms of reducing the risks of falls, assaults, or any other crimes likely to happen in such an isolated and unlit area. Detailed cost estimations were also made for each problem area. These specific improvements for the Brentwood pathway were priced out to be around $195,000. Next slide, thanks. So in order to finalize these design elements, they were then examined again through that utility function. As shown in the inputted value column, we now have 300 meters of a paved sidewalk instead of the crumbled pathway, and 65 meters of a paved sidewalk instead of the steep mulch pathway. The utility analysis also takes into consideration the concept of snow clearing and the new lighting along the path. And these new improvements, they caused a reduction in utility function societal cost of $1.34. Now, just to gain an idea of which improvements cause the biggest difference in societal cost, we can take a look at this chart. A negative value represents a decrease to societal cost. Sorry. Looking through each of these improvements, the element that gave the greatest decrease would have the greatest benefit. And based on this chart, the new streetlights gave the greatest benefit to societal costs. So the final step was putting this area into TRANSCAD. And in TRANSCAD, we can calculate the traffic flows and the utility value for every link in the system. The Brentwood map on the left, it shows the current estimated pedestrian flows in red and the estimated traffic flows after the improvements in black. So with the existing conditions, the traffic flow is currently 572 people, but after the improvements, the traffic flow increases all the way up to 904 people. So the map on the right shows the utility value cost per person. The value in red is the current utility cost of $2.32 per person. And with the improvements, it drops all the way down to 67 cents per person. So just note that the utility value mentioned in this slide is not the exact same as the previous slide, because the improvements that were mentioned in the previous slide, they account for more than one TRANSCAD link. So I will now pass it on to Morgan to talk about our 2 other areas.
Thanks, Ala. So I'm going to talk about these 2 other problem areas. I won't go as in-depth as Ala did, but I'm just going to summarize the proposed solutions and improvements that we did. So the first area is 32nd Avenue, which is just north of the U of C. And there's a clear desire line beaten into the ground in this location. Many people frequently walk on this pathway as it is inconvenient for pedestrians to cross the 4-lane road, walk through the family housing parking lot on the right, and then back over. They just cut across there. This is a regular, bumpy, uncleared in the winter, and has no protection from adjacent vehicles traveling at 60 kilometers per hour. So we suggest that for the immediate action for this pathway is to lay down temporary matting to instantly improve the walking conditions for relatively cheap cost. For the long-term plan for this area, we propose a concrete walkway be constructed with concrete planters along the road to add to this to the City of Calgary's snow clearing plan. The planters serve to create separation from the roadway, which increases the perceived safety of the pedestrian, and to beautify the area. These changes correlate to a decrease in dollar value of the trip cost from $12.63 to $9.86, all the way down to $5.11 for the final plan. These factors, the factors that this decrease comes from is primarily due to the facility type, which is just upgrading the path, with also a large portion coming from the added snow clearing. So the second area, another area that we examined was the MCMAHON Stadium pathway, which is just south of the U of C on the west side of MCMAHON Stadium, and this view is to the east. There exists a gravel pathway shortcut between the University of Calgary, or the University Drive, and University Heights. Many people use this pathway to get from the bus stop behind the building on University Drive to the community shopping area and Foothills Hospital behind. This path is not well kept, not well lit, and is not accessible by those who are differently abled. Wheelchairs cannot access this. The immediate plan would be to do some regrading of the area and to make the path less steep and then pave an asphalt pathway. The path should also be added to the snow clearing plan so there isn't as treacherous in the winter. For the long term, we propose that lighting and a railing be installed, aiding in safety when walking at night and having something to grab at in the winter. This brought the cost per trip from 66 cents down to 60 cents, all the way down to 18 cents for the full plan. The major factors contributing to this decrease was snow clearing, the improvement of the quality of pathway, and better lighting. And this brings us on to the findings of the project. So when calculating the social benefit cost of this project, we need to ensure that we had all the information necessary to provide a proper investment benefit analysis. We calculated the total benefits for this network each year based on the volumes expected and the utility days per year based on when the network is being utilized, which mainly coincides with the school year. The investment cost was calculated by conducting a detailed cost estimation with all of the proposed improvements. The net present value of the investments and benefits was then determined by discounting the 2020 dollars, and the payback period of each plan was also calculated. We based the immediate, intermediate, and long-term plan on a 1, 5, and 15-year implementation period with a 5, 10, and 15-year lifespan. One moment, sorry. So this, for the proposed plans, the predicted dollar benefits per day were $942, $3,441, and just over $5,000, with a gold standard, the ideal pathway, coming in at almost $69,000 per day. When calculated over the year, you can see the benefits of the improvements outweighs the investments for the immediate and intermediate timeframes, but not in the long term. This suggests that there are only marginal gains associated with the long-term solutions, as the main issues have already been rectified in the immediate and intermediate plans. When calculated over the 5, 10, and 15-year lifespans of each plan, we can see that the solution pays for itself multiple times over. In reality, however, these improvements could last much longer than the lifespans used in our calculations. Now, with the gold standard that was touched on earlier, this is the benefit from the ideal pathway. We're still a long way to go to reach this, but it'd be very costly to ensure every single pathway in the network has perfect lighting, snow clearing, and new concrete. However, this does show that there's large room for improvement for the network as a whole to reach the gold standard. Like most projects, the only limiter is budget, which is why it's important to determine where an improvement should be made and what type of improvement should go there that will maximize this benefit. So finally, looking at the contributions from each factor to the total benefits seen for this network, we can see that crossing type and facility type are the greatest contributors to the benefits, with quality of path and lighting being of lesser importance. However, this is not a standard generalized proportion. This is specific to each network and the specific needs of that network. This area clearly benefits from the increased quality of road crossings and the installing of new walkways that did not previously exist. For the most part, these areas were fairly well lit, so lighting ended up being less of a factor. By determining the main contributing factors for the network of study, treatment options can be prioritized to ensure the network receives the maximum benefit possible. So now I'm going to hand it off to Sad to give some potential applications for this process.
Yeah, thanks, Morgan. Overall in this project, we kind of blended research work as well as design work and created this method for evaluating pedestrian networks as well as applying it towards our design. In the next part of this presentation, we'll go through some possible applications of this project. One of the things that excited me most about this method we created is the asset management applications of our project. Normally, it is really hard to determine what areas have poor pedestrian experience using a data-driven approach. For example, in our project, after doing some research about the current conditions in our study area, we proceeded to pick problem areas to investigate based on areas we perceive to be in poor pedestrian conditions, as well as having high pedestrian flows. The problem is, in all honesty, we had no idea if we picked the best areas to investigate, as there might be areas in poor conditions and with high pedestrian flows that we overlooked, or we might have picked areas that we think are in poor conditions, but have very, very low pedestrian flow, so it doesn't really matter. Or there might be places that are already in pretty good condition, relatively good condition that we decide to investigate. So to deal with this issue, we came up with a parameter that quantifies poor pedestrian experience. And we call that parameter utility increase potential. Utility increase potential is how much societal benefit will be provided if the link is upgraded to the best possible link, the best possible conditions, or the gold standard. So if we can upgrade it to a link that has 30 meters light spacing, snow clearing, and the best facility type and the best quality. Utility increase potential is quantified as the current utility link cost in the dollars per trip minus the gold standard link cost in dollars per trip divided by the length. The units of utility increase potential are dollars per 100 meters per trip or cents per meter per trip. And higher values signify worse pedestrian conditions. The reason this parameter is normalized for length is so that longer links and shorter links can be compared. The map on the slide shows the utility increase potential of all the links in our study area. The lower utility increase potential, or the best current pedestrian experience, is shown in yellow and is clustered in the area around the University of Calgary, as outlined by the red circle. Paths in the University of Calgary tend to have good lighting, tend to be in good conditions, theoretically have good snow clearing, and tend to have utility increase potentials below 5 cents per 100 meter per trip. That means even if I wanted to improve it the best I can, I put $1 million per meter on it, based on our model, we'll only be able to increase the utility societal cost by up to 5 cents per 100 meters. On the other hand, varsity, as shown in the yellow square, tends to have much higher utility increase potentials. As the pedestrian experience in varsity is much worse because of the lack of lighting, the lack of pedestrian infrastructure such as sidewalks, and most of the paths in the areas tend to have utility increase potential over 50 cents per 100 meter per trip. Note that utility increase potentials over $1 per 100 meter per trip, shown in blue, are not very common and are mostly for grass paths. Using utility increase potentials, we have a data-driven approach to provide an apples-to-apples comparison of pedestrian experience and can easily be integrated into a GIS system. As utility increase potential is independent of pedestrian flows, you do not need to play around with TRANSCAD or estimate traffic flows or estimate OD matrices or anything like that to calculate utility increase potential. This parameter and map would be useful to the city to determine areas that are in need of pedestrian improvements and areas that are worthwhile investigating. Just to clarify the concept of utility increase potential, we'll go through an example. If I have a grass trail along a major road with streetlights at 125 meter spacing, which is normal along major roads around the city, with no snow clearing, the societal cost of traveling that path is 1.543 cents per meter, or $1.543 per 100 meters per trip. For paths along major roads, the lowest possible societal cost possible for a path using our utility function parameters is 0.351 cents per meter, or 35.1 cents per 100 meters, which is for a paved sidewalk, which is separated from the major road with a median, with street lights at 30 meters, which is the distance that pedestrian scale lighting is often spaced at, with snow cleared by the city. So for all major roads, for all paths along major roads, whether it's along 32nd Ave or 16th Ave or whatever, the gold standard utility is 35.1 cents per 100 meters per trip. For all pedestrian crossings of minor roads, it's 14 cents per crossing. it's fixed depending on your facility type. The utility increase potential, or the maximum amount of social benefit we can gain by upgrading the path, is the current societal cost of 1.53 cents per meter minus the gold standard societal cost of 0.351 cents per meter, working out to 1.192 cents per meter, or 1.192 dollars per 100 meters per trip. As we noticed in the previous map, having a utility increase potential of over $1 per 100 meter per trip is not very common. This means that this path, if this path existed, is in probably one of the worst, is in very poor conditions relative to the other pedestrian paths and pedestrian infrastructure in our system. Next, please. So utility increase potential is really good at determining which areas have a poor pedestrian experience. It provides an apples to apples comparison. So in a way, I can compare the pedestrian experience on a sidewalk along a minor road to a sidewalk along a major road to a crosswalk. However, the utility increase potential does not account for traffic flows. Two identical paths with exactly the same parameters will have the same utility increase potential, even if one path has 1 user per day and the other path has 10,000 users per day. Now, in order to deal with this issue, we came up with another parameter we call gold standard improvement benefit. The gold standard improvement benefit is the utility increase potential multiplied by the pedestrian flows, providing a value as $1 per 100 meter per day. This tells that if I improve a path to the gold standard, how much societal benefit will I gain per 100 meters of path distance if the pedestrian flows do not change? This map would be useful in prioritizing investments by focusing on areas with gold standard improvement benefits, as they will provide the most benefits for the same amount of length. Another reason we also we're dividing by length here is because the cost of many pedestrian infrastructure, such as adding lighting or adding paths, depends on length. So areas that have high improvement benefits, such as the areas in red, that have over $1,000 per 100 meter per day, such as near the LRT stations, by putting the same, by paving 100 meters of path, you can get much higher improvement benefits than trying to pave a 100-meter path on a path that has an improvement benefit of $1 per 100 meter per day. I'll pass it on to Zach to talk a bit about kind of the lessons learned and so some of the personal stuff we learned over this project.
Thank you very much, Thad. Hello, everybody. I'm Zach, and I'll take you through the lessons learned and the current future of this project. Now, we definitely learned a lot about transportation and ourselves during the project. We had many takeaways, but for the sake of time, I'll only talk about 3. Now, learning new software is always a little bit of a challenge. Sometimes we encountered problems where one member of the group would have trouble with the new software, but as they were the only ones that was prepped on it, it made it really hard for us to get help and for them to get help on the issue. Holding software information sessions with the team at the start of the project would have been useful so that all team members could help with any of the project tasks as needed, instead of having kind of certain individuals a lot more focused on certain aspects and certain programs, which kind of led to there being a bit of a disconnect between our team. Another one of the smaller things we learned early on was due to us being such a kind of a team-driven group from the start, having get-togethers and games and such, it allowed us to have a strong group dynamic even during high-stress situations. Now, this taught us a valuable lesson in team building, with seeing that the dynamic was actually able to continue to be strong when we were under kind of crunch time or some kind of hard stress. And we were shown that with a proper group and with a good kind of working group, it's easy to work under pressure. And finally, our biggest takeaway. Now, it's important to clearly define what the client has in mind for the project at the start. Adding the TRANSCAD model changed almost entirely the direction of our project, from designing a pedestrian plan to creating a methodology to analyze these pedestrian plans. If we had known earlier on that this was going to be the goal of the project, learning TRANSCAD could have begun way earlier, and we would have been able to use kind of more robust techniques to develop plans and analyze the project. Which then brings us to this slide, if not for our deadlines. Now, again, we would have loved to have used a more of a iterative approach to design of our pedestrian plans, but due to the time constraints that we were given for the project and our change of focus near the end, we had to take a bit more of a direct approach to things, which I think overall we would have benefited from a kind of a more iterative design approach had we had more time, but our project worked out either way. Which brings us to who can benefit from our project. Well, firstly and hopefully, all the pedestrian users in and around the U of C will benefit from our proposed changes. It'll also provide smaller benefits such as increased physical activity, improvements to safety, allow for easier access to surrounding areas, and hopefully reduce air pollution from more people walking instead of driving. Second, future land developers who want to focus on a more active transportation plan can use our design principles to help deal with surrounding infrastructure and decide how best to develop the land. Additionally, the City of Calgary can use this for any future development plans in existing neighborhoods, as we did for neighborhoods such as Varsity and Brentwood Station. And finally, future students or transportation engineers looking for general analysis of pedestrian networks would also find use of our information within this project. Which now brings us to the what is happening with our project section. So we're currently taking the project in two-ish different directions at the moment. From the suggestion of our project supervisor, Dr. Hunt, we are working on turning our final report into something that we can publish within an engineering journal. As he recommended, it would be a great way for us to get our names on a published piece of work. Second, our project supervisor, Dr. Hunt, is also using the Baojing code and data we collected during our project to further research walking utility with his company HBA Specto, which the results of that we'll be seeing at a later date. And with that, that concludes our project. We will be taking questions in the chat, and all of our group members will hopefully be able to answer any questions you guys might have. And thank you very much for watching our presentation.
Thank you all for that wonderful presentation. Are there any questions? There's some questions from the chat. I guess I'll read them out as opposed to getting them online. Saeed was asking, what demand data did you use for the long-term plan?
So in our methodology, we use the same origin destination matrix for our current plan as we did for our long-term plan. The reason our traffic flows changed is because we assumed that people travel along a minimum societal cost, a minimum cost path. That means in our case, because we improved the Brentwood path, we dropped its cost so much that it diverted people from other paths onto the Brentwood path. That's why the traffic flows increased on the Brentwood path. We assume the origin destination matrix will be exactly the same between now and the long-term plan. It's a bit of a conservative estimate of the societal benefits.
Great, thank you. Next questions from Chun. Any considerations to convert 32nd Avenue from 4 lanes to 2 lanes and use additional space for bike and walkways?
We did. One of our ideas for 32nd Avenue was to actually redesign it to match more of a realistic urban boulevard, because it is classified as one, but it doesn't look like one. So that was to add in the bike lanes and all of that extra stuff. But the biggest issue with doing that was the cost. It was a very high price range. And the other issue was that we had a limited space amount to do that. So just to address like switching it into 2 lanes instead of the 4, the reason why we didn't take that one into an option was because it was a high traffic flow in terms of vehicles. And that's why we wanted to keep it at the 4 lanes and try to add in the extra bike lanes. But unfortunately, because of space and cost, it wasn't a feasible option.
Great, thank you. Next question is from Ahmed Ali. With a large team and each of you having your own schedules, how difficult was it to work as a team? Did you guys divide tasks for each team member or group of team members? And also congratulations on a really very useful and in-depth work at the capstone level.
I can talk a little bit about it, and I think my group members can add on to it. So what we did as a team was the big advantage is because we were all in civil engineering, a good chunk of our classes are common. So what we were able to find times where we were able to meet. So we decided to set up our meeting time 8:30 in the morning on Tuesdays. And once we did that, we started to split our team into sub-teams. So our first task was to build a proposal. So what we did is we split half the team to go and start writing up the proposal. Well, we split the other half of the team to start, inventorying our area. So over time, we kept on splitting into sub-teams and dividing the tasks that way. The other thing is we really kept in contact using Facebook Messenger. So we were like always up to date with each other. Do my other team members have anything else you guys want to add?
Well, to add on to that, at the very beginning of the project, we took all of our class schedules, and I think we all emailed them to either Morgan or Cassidy, and we basically created an entire chart of when everybody was busy, and we looked at all of the gaps that we all had in our schedules to determine when we were going to meet up and when we would be free to either plan things out or talk things out or work on the project or work on splitting things up. And then from there, like Saad was talking about, we split up into smaller groups in order to tackle certain sections, which was both a good thing and of course kind of both a bad thing, because it meant that only certain groups were overly familiar with certain sections. But I feel like overall in the end it was definitely the right choice for us to split off like we did, because it allowed us to tackle a lot more issues at once and really get the project kind of completed at a faster rate than we would have if we'd all tried to work on the same thing.
And also as a group, like we were very, it seems like, we are a very friendly group. We all work together really well. And there was a lot of initiative taking. Everyone was willing to take initiative and take on tasks. It wasn't, you didn't have to force anyone to do anything. Everyone volunteered to do it.
Excellent. Another question from Ann Coffin. Were you able to quantify the benefits of completing part of the pedestrian network that was not previously in place?
So for that one, I think that kind of pertains to our utility function. For us, I think that could be an option, taking an area that just doesn't have any pedestrian facility there and adding that into our calculations in our survey to find out what the user cost of an area with no pedestrian facilities would be. We didn't quite include that in our analysis, but I think it definitely could be factored in terms of determining the user cost and comparing it before and after. The closest thing I think we did have is sort of in terms of our facility type, we did have no lighting, we did have no snow and ice clearing, but we didn't have a no path. The closest thing that we had was the grass trail path, like we saw in Brentwood with Ella's, that was Morgan's and Ella's also. But with those areas, there is a little bit of a desire line there. So there wasn't anything in place, but there was sort of still that little like mulch. A million people have been walking through that area. So we do kind of have it. You could formalize it a little bit more as an undeveloped, completely undeveloped, no grass trail or anything in a future application though.
So if I'm not mistaken, I believe, or the question was, were you able to quantify the benefits of completing part of a pedestrian network that wasn't previously in place? I think a good example of this would have actually been what we did with 32nd Avenue. So we have the path that runs along the road where at the time well, currently right now, if you walk out there, there is no pathway and there's no real actually infrastructure in place. There's just that desire line along the dirt that shows that people want to be walking there, but right now there isn't actually any infrastructure there because all you're doing is just walking along the side of the road on that kind of grass path. So that was one of the chances that we took with there is no path, there's no sidewalk, anything. We're actually basically creating a new pathway through this area. And I believe that there was a couple of other desire lines that we saw within Research Park, kind of to the east of Varsity, where you could see a couple of lines going through a few fields. And I believe that the reason that we didn't consider that was that it either wasn't a part of the city property or University of Calgary property, I believe, and it was private property, so we didn't really want to kind of get involved with touching that. But I think we actually did consider it anyway, and the resulting utility benefit was not kind of worth it in terms of other plans.
Also with TRANSCAD, you know, kind of adding on to what Catalina and Zach were talking about, TRANSCAD assumes that pedestrians can only travel on the links you made. So TRANSCAD can't find the desired line for you. Like if there's a unauthorized path and you don't make a link for it, no pedestrians will take that path. Also, TRANSCAD can't identify jaywalking unless you make a link that allows people to jaywalk.
Okay, thank you. Another question from Tony Churchill. The link closer to the stadium is on private land and the owner may not want to encourage more pedestrian traffic, even though we know there is a huge demand during events. Any thoughts about the perceived disbenefit to adjacent landowners and how to quantify this? The paths through grass indicate that there is a utility for an unimpeded route, even if there is no specific enhancement for them.
So I think for this one, in terms of the utility function, what happened with ours is our sensitivities are based on our responses, but in a broader application, you could potentially, you know, include the responses of landowners, adjacent landowners, and get their perspective on the utility and how that would affect the utility values for them. So there is the possibility and the structure in place to address their utility and disbenefits for them.
And regarding the, go ahead, please.
Go ahead, Zach.
Oh yeah, and regarding the paths to grass, indicate that there is a utility for an unimpeded route, even if there is no specific enhancement for them. Yes, there is a utility function value for grass trail. So if you have a grass trail along a major road, it had a pretty negative, it had a pretty high societal cost. But a grass trail along a minor road, its societal cost wasn't nearly as high. So so yeah, there is for sure a utility for even a grass, even for a grass. Just if you're along a major road, it's pretty bad. Pedestrians don't like it.
Well, thank you, everyone. I guess that's the amount of time that we have. It's about 1 minute to 1 o'clock. Just a few comments of congratulations. Very impressive work from Saeed S. Very impressive. Tony Churchill, thanks. And excellent work. And Coffin, great project. No, you guys did a very good job. Very good presentation. Thank you all.
Thank you very much, Lou.
Thank you.
Thanks for having us.
Thanks everyone for taking the time to learn a little bit about our work through this past year.
Wish you all the best.
Thank you.